Okay, in this video I'm going to continue on my tutorials in thermodynamics and statistical mechanics. In video number 26, and we're going to come to where we have just come to a very important topic in physics in general, because thermodynamics is so important, and this is so important and fundamental to thermodynamics. We're talking about entropy. So the placeholder we give for entropy is S. Now, in previous videos I've discussed the second law, and I discussed Einstein Solids, and I also discussed ideal gases, and I proved formulae for the multiplicities of both and the multiplicities of interacting Einstein Solids and interacting ideal gases. So it's from there that I'd like to begin. In video number 25, which was quite brief in fact if I think about it, but the reason it was brief is because I did a lot of the work in the previous videos, we can say the following: any large system in equilibrium will be found in the most likely macro state. And we define the most likely macro state as that which has the greatest multiplicity. Okay, so that's what we saw in the last number of videos. We kept seeing this Gaussian function. We kept saying that the multiplicity is equal to the maximum multiplicity multiplied by this Gaussian function. And because the numbers were so enormous, we saw that in order for the Gaussian function to exist, if we plotted, we'll say, the multiplicity versus the energy in one of our solids, we saw that it was zero for almost all energy values except for a very small range of energy values, so, set around the total energy over 2. In other words, set around half of the total energy. In other words, if you have two solids interacting, the system will stop sharing energy when both of the systems have exactly half the total energy. But when we plugged in numbers, and I just said the numbers, I said that, for example, if you were to plot, let's say if you were to literally plot this as it is, so this, you might say this distance is a centimetre. So you might say that the Gaussian exists for a centimetre. Then to go from one end to the other, or from one end of the Gaussian into the centre, might be thousands of kilometres. Okay, so the point is, there are thousands of kilometres of states here, each of having zero multiplicity, and then they get up to like a centimetre of states which has non-zero multiplicity. So let's paraphrase the second law. We can say that multiplicity tends to increase. Let's paraphrase the law. Okay, we said that this is the general term of the second law of thermodynamics, and I said it wasn't a fundamental law but more a statement about probabilities. But it's very important, and it seems to work everywhere that we know of. So now let's move on to entropy. So we said that, what sort of parameters did we have in the multiplicity function? We had Q, we had the energy, we had the number of particles, and so on. But if we think about a single mole, like when we talk about even a single mole of particles, or Avogadro's number, we have millions of particles, we have billions of billions of particles. So the numbers are absolutely, they're stupendous. So in the previous few videos we saw how we deal with enormous numbers and how to manipulate complicated functions. Well, we immediately try and take a logarithm. So let's say we have our multiplicity, and I take the logarithm of our multiplicity. Okay, that turns an extraordinary large number into an ordinary large number. So like I said, we'll say we're going to define this as being the entropy, the natural logarithm of the multiplicity function. Okay, that's it, nothing more. So you might just say that the entropy is the multiplicity. You could paraphrase it in your own head. Entropy is multiplicity, or entropy, S, is the natural logarithm of the multiplicity. It's the natural logarithm of the total number of states available in the system. Okay. Now, for reasons we'll see later on, and for historical reasons, we give it a unit. We give it dimensions, or we give it dimensions, because of course the natural logarithm of something is dimensionless, but we give it a unit, and we do that by multiplying by Boltzmann's constant. So the units here are joules per Kelvin. Why would we do this? Well, I can't really answer that yet. You'll see in future videos, but essentially the reason is it allows us to evaluate thermodynamic quantities very, very easily because of the units of Boltzmann's constant. It's great. It allows us to use entropy and make entropy a fundamental quantity in thermodynamic analysis. But if we want to actually understand entropy, I suggest leaving out Boltzmann's constant. So when you're trying to just, come across it or come to terms with it in your own head, think the following equation, which is incorrect, but think the following equation. Think that entropy is the natural logarithm of the multiplicity. So in words, entropy is the logarithm of the number of ways of arranging things in a system. And we, of course, multiply by Boltzmann's constant, which for the moment I'm going to leave out. So the logarithm, as I've said, turns a very large number into an ordinary large number. So like I've said a few times at this stage, we're going to leave out k, but we should leave it there. But we're trying to come to terms with what it means, so we'll leave it out. Alright? So we say entropy is the natural logarithm of the number of states. So why do people say then, why do people say that it's the disorder? Well, think about it. Because entropy is the natural logarithm of the multiplicity, and we said that in the second law of thermodynamics, the multiplicity tends to increase. Well, because the multiplicity tends to increase, and multiplicity is exactly what entropy is, that means entropy tends to increase. Entropy tends to increase. So you can paraphrase the second law as follows. Well, you could fully say the second law is any large system in equilibrium will be found in the most likely macro state. Full stop. Paraphrase it, you will say the multiplicity tends to increase. Paraphrase it again, the entropy tends to increase. Okay, so we call it the law of increased multiplicity or the law of increased entropy. But why call it disorder? Why do people think about it in terms of disorder? Personally, I don't like thinking about it in terms of disorder, because one man's order is another man's disorder, if you look at people's bedrooms perhaps. But the reason is as follows. When we think about disorder, we think about more states. Disorder, I'm going to say that disorder equals more states. So if you have increased the number of possible states, you have increased the disorder, or you've increased the multiplicity. So in order to increase the number of states, or in order to increase the disorder, you must increase the number of states, or increase the multiplicity. Well, how do we do it? So let's go ahead and take an example. So I'm going to plug in the actual equation. S is equal to k natural logarithm of the multiplicity. So in previous videos we showed that the multiplicity of an Einstein solid is equal to EQ over n to the n, where n was the number of units of energy in the solid and the total energy was equal to Q times h nu. But I'm just going to ignore h nu for the moment because look, it's only a constant. So let's get the natural logarithm of it and so on. So we get S is equal to k times the natural logarithm of EQ over n to the n. Alright, so we could rearrange this by saying that S is equal to n times k times the natural logarithm of the log of Q over n plus 1. It's not very important to rearrange it that way, but that's the way we're going to rearrange it. Now, like I said, second law of thermodynamics, paraphrase, says entropy tends to increase, or the disorder tends to increase. So how do we increase the multiplicity of this particular state? Well, we can increase n, or we can increase q. So we're saying that if we increase q, we increase the total number of states, we say we've increased the disorder of the system. If we increase the number of particles, we say that we've increased the number of states, or increased the disorder of the system. So in general, we say disorder, if you've increased the disorder, we've increased the number of states. So if we look at our Einstein solid, the only way to increase the number of states or the disorder is to increase n or increase q. Alright, but just a matter of interest, let's plug in some figures. Say the total number of particles here is 10 to the 22 and q is 10 to the 24. That gives us 0.7 joules per Kelvin. Okay, so we have S, the entropy is 0.7 joules per Kelvin approximately. So I'll just try and rephrase that again. So generally, the more particles that there are in the system, the more energy it contains, and the greater its multiplicity, and therefore the greater its energy. Besides adding particles and energy, you can increase the entropy of the system by letting it expand into larger space, breaking large molecules apart into small ones, or mixing together substances that were once separate. In each of these cases, the total number of possible arrangements increases. So each time we think about increasing that disorder. But although I've concentrated on talking about disorder, the only reason I've done it is because other people think about it that way. I prefer just to think about it as the natural logarithm of the number of states. And I try not to use the phrase disorder. But I'm sure you've heard it. I'm sure that's what your physics teachers would have said to you. That disorder or entropy is entropy tends to increase, or entropy is disorder. Okay, so are there any interesting properties of entropy? Yes, there's one particular one I'd like to show you. Remember that in most cases we discussed systems that were independent of each other, and thus the total multiplicity was the product of the individual multiplicities. We know that the multiplicity, or the entropy, is k times the logarithm of the total multiplicity. So it's k times the logarithm. What am I doing? It's k times the logarithm of the a and the multiplicity of b, like that. Using our rules of logarithms, that's k outside the natural logarithm of the multiplicity of a plus the natural logarithm of the multiplicity of b. Or if I want to just put in the value of k there, or the factor of k, and we can rearrange this as the total entropy is the sum of the the sum of the individual entropies. And that's a very neat property. Now it only works, and it's very important, it only works where the total multiplicity is the product of the individual multiplicities. And we have seen states, well, you may or may not have watched my quantum statistics videos already, but there are plenty of systems where the multiplicity is actually the sum rather than the multiple, or the sum rather than the product. So this only works where the multiplicity multiplicity is a product. However, in general, you can just say that this is the case, because the numbers are just so enormous that saying it's a sum versus a product is not really a big deal. Okay, so what else can we say? So just once more, entropy tends to increase. Okay, so that if you were to graph entropy versus some variable like the energy, you'll see that the graph is allowed. If the graph is allowed to fluctuate, it will generally not have a very sharp peak. But taking a logarithm smooths out the peak that was present in the multiplicity function. So let's just try and explain that. So let's say when we plotted multiplicity versus energy, let's say we plotted Q sub A versus the total multiplicity, and this was in actual fact a ridiculously sharp peak like that. But when you take the natural logarithm of it, what we end up doing is smoothing it out. So you might get something that looks like that. So if you plot, for example, entropy versus energy, you mightn't get this particularly ridiculously pointy or sharp multiplicity function. Now I'm not going to talk about anything more. I'm not going to make it any more complicated than it needs to be. So we're going to leave it at that. That entropy is the natural logarithm of the multiplicity. It's the natural logarithm of the number of ways of arranging your system. And we multiply by Boltzmann constant to give it really nice units. Okay, so thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.